Drew. In this calculus video, I'm going to introduce the concept of infinite limits and work through 5 examples to help you complete your homework and understand this concept. As we go through our examples, you're going to start to recognize that you've seen this before. Back in Algebra 2 and even in pre-calculus, you studied how to graph rational functions. And in rational functions, you looked at and sometimes found slant asymptotes or oblique asymptotes, you found horizontal asymptotes, and you found vertical asymptotes or holes. Well, that's kind of what an infinite limit is. It deals with vertical asymptotes. A limit in which f of x increases or decreases without bound as x approaches c, a particular value of x, is called an infinite limit. Oh, by the way, before we finish this, you have this idea of limits at infinity, the limit of the function as x approaches either negative or positive infinity, and that's your horizontal asymptotes. The oblique asymptotes don't ever settle into some kind of constant real value of y, so we're talking about the horizontal asymptotes. But x is not approaching infinity, x is approaching a particular value on the x-axis, and the graph is increasing or decreasing without bound. Well, there's your vertical asymptote. Let f be a function that is defined at every real number in some open interval containing c, except probably c itself. It's going to be undefined there. I say, we're working the possibly. This is the beginning value, the beginning stages of calculus, and mathematics can get quite complicated. As I've already started to learn doing these videos, I'm sometimes getting questions that after 17 years of teaching high school, either I know I never learned or I've long forgotten from my studies of mathematics in college, so it gets quite complicated. So we'll just say, that the function again is going to be defined at every real number in some open interval containing c, except possibly c itself. For our examples, it's not going to be defined at c. Then we'll have our vertical asymptotes. The limit as c approaches c of f of x is equal to infinity. This states that for each m greater than 0, there exists a delta greater than 0 such that f of x is greater than m whenever the difference between x and c, the absolute value of that difference, because we can only be taught measuring distance in positive values, is between 0 and delta. I'd like to talk through these formal definitions to hopefully make it a little bit easier to read what your textbook, your calculus textbook, is giving you with these very formal definitions. We're not going to prove this, we're just going to do some algebraic examples. So for my video, I guess for the examples, this is a little bit of overkill, but it never hurts to make sure you can read the textbook. What this is saying, this states that for every m greater than 0, so we're moving sort of, in this case, we're talking about increasing to positive infinity, so we're increasing without bounds, so we have an m that is positive. There exists a delta greater than 0, so our delta is the difference between this vertical asymptote, the horizontal distance between our vertical asymptote and the function itself, such that f of x is greater than m, so the function is going to take a value above whatever this real value of m is, so we're increasing, whenever we pick a value of x such that the difference between x and c is less than delta. So basically what that's saying is, I've identified this value of x here, and I'm going to put x because I'm going to have it be fluid, and if I allow this particular difference, which right now is delta, if I pick an x within this interval such that the difference between the x and c, or sort of creating a new measure of delta, if you will, that the absolute value of x minus c, if it's less than the horizontal distance of delta, the function is going to take on a value, an f of x value, that's greater than m. So basically, as I get closer to the value of c, where we have this vertical asymptote, the function is going to increase without bound and thus have an infinite limit. And this language down here in orange is just the notation for the function decreasing without limit. So maybe, every time you have a vertical asymptote, the graph doesn't necessarily shoot up, and it actually doesn't even have to go in the same direction on both sides. Sometimes the graph will go down and then increase without bound on the left and right-hand side of the vertical asymptote. So I got a little bit more to say as far as the formal definition here goes. So let me leave the picture up here, erase this definition, and add just a little bit more before we get to our examples. To define the infinite limit from just the left, replace 0 is less than the absolute value of x minus c, which is less than delta, with c minus delta, which is less than x, is less than c. So you're approaching c from the left, and you're analyzing the behavior of the function as you approach that value. If you want to define the infinite limit from just the right, replace, again, this expression with c is less than x, which is less than c plus delta, where your x values are greater than c, and you're coming in towards, again, that this value of c, and you're looking for that unbound behavior of the function going up to infinity or down to negative infinity. Okay, we will be able to say, just like before, if the limit approaching the left is the same as the limit approaching the right, well, kind of let the limit sort of exist, but we're not really. Actually, we're saying that, sometimes the limit of f of x as x approaches c is either positive or negative infinity, but what we're actually showing is that the real limit fails to exist. A real limit, again, a real y value that the graph is approaching from both the left and the right. Could be an actual value where the function is defined, or it could be like a hole, where the limit is approaching some real y value, but the function itself is undefined there, or the function itself could be actually defined, at some other value of y. But we're showing that the real limit fails to exist. So we're going to be saying, it's sort of weird to say that the limit of f of x is either infinity or negative infinity, and we're saying that, the section's called infinite limit, but we're actually showing that the real limit doesn't or fails to exist. Now, sometimes we're going to even say that the infinite limit doesn't exist, because just like with real limits, the left and right have to be equal. So if it approaches infinity from the left and approaches negative infinity from the right, as it approaches this vertical asymptote, then we're going to say that there is no infinite limit either. But if it approaches infinity from the left and infinity from the right, or negative infinity from the left and negative infinity from the right, if those left and right limits match, then we will say that there is an infinite limit. It is either positive or negative infinity, but we're really saying that there is no real limit. Or, again, we will also be saying, of course, like I just said, that the infinite limits will fail to exist if the left and right are not the same, just like with real limits. Definition of a vertical asymptote. I keep talking about it. What does the definition say? If f of x approaches either positive or negative infinity, as x approaches c from the left or the right, then the line x equals c is a vertical asymptote of the function f of x. Theorem. Let f and g be continuous on an open interval containing c. If f of c is equal to, not equal to 0, and g of c is equal to 0, and there is an open interval containing c such that g of x is not equal to 0, for all x not equal to c in the interval, then the graph of the function given by h of x is equal to f of x over g of x, has a vertical asymptote at x equals c. Okay, so I've highlighted a couple of key points of this theorem. First of all, if your numerator, f of x is in the numerator, if your numerator and denominator are both equal to 0, in our rational functions, we're going to be doing a lot of examples with these rational functions, you are probably going to have, if the numerator and denominator are both equal to 0 at the same time at the value of c, what's probably going to happen, especially if it's just a pure algebraic rational function, is that's being created by common factors that are both in the numerator and denominator that are going to cancel out. You'll see that as we do our examples. Things get a little bit more complicated when you have trig functions in your rational functions. Thus, we're saying, that we'll probably have a hole at c. Some craziness can happen as the function gets more complicated. And this little part here in green, such that there exists an open interval containing c such that g of x, our denominator, is not equal to 0 for all values that are not equal to c. We're just trying to, identify the asymptotes one at a time. Functions can have more than one asymptote That is not really that uncommon to have two or more vertical asymptotes, but we're going to just try and identify one of those at a time on these open intervals. Okay, so we got 5 examples, a lot of algebraic examples, some with a little bit of trig. We got 5 and they're coming up right now. First example, find the left and right limits. Part A, I'm specifically showing you that I want the left and right limits. In my second example, I'm just saying find the limit as x approaches 4. In both of these examples, we have denominators which are going to become 0 when we try and approach 3, and they're not going to cancel out in any fashion. So this one, not having an indication of left or right, but just says find the limit as x approaches 4, you're going to have to understand that you need to find those left and right limits and make sure that they're equal. Okay, so if you remember graphing rational functions, these just are nice algebraic rational functions, and we have a polynomial in the numerator and denominators, that if the top degree, which is a constant, so the degree of the numerator is 0, and the degree of our denominator is just simply x minus 3, so the degree is equal to 1, and from algebra pre-calculus we learned that when graphing rational functions, if the denominator had a degree larger than the numerator, then we had a horizontal asymptote of y equals 0. So as I test to see what's going on to the left of 3, when we have a denominator that's undefined, we talked about already finding limits with a numerical or graphical approach. So I don't want to do an entire table of values getting closer and closer and closer to 3 as we approach from the left. I'm just going to pick one value that's just to the left of 3, test it, see what's going on, and knowing that this x minus 3 is going to be 0 at 3, making this undefined, making us a vertical asymptote at x equals 3, I know I'm not going to cross that vertical asymptote. So if I get a value that's very, very negative, I'll know I'm approaching negative infinity. Or if I get a value, I'm going to plug in 2.9. If I get a value that's positive and very large, then I know I'm going off to positive infinity. If you want to be sure, you can test a few points, make those tables like we learned about finding limits in a numerical approach. So I'm going to plug in 2.9, do a little scratch work here. So we have 2 over 2.9 minus 3. That's going to be 2 over negative 0.1, and that simplifies out to be negative 20. So I have a horizontal asymptote at y equals 0, and then as I get very close to 3 from the left, I'm going down. So this left limit is going to be negative infinity. And as I approach 3 from the right, I'm going to just plug in just to the right of 3, so it's going to be 2 over 3.1 minus 3. That's going to be 2 over 0.1, and that comes out to be positive 20. And again, like I said, if you're not sure what's really going on, by plugging in just one value just to the left and right, then get a little bit closer. Try 2.99 and maybe, 3.01. And, make sure that the behavior you believe you're seeing is actually it. Now, in this first example, our left limit is negative infinity. Our right limit, as we approach from the right, is positive infinity. So the two-sided limit, the limit as x approaches 3 of 2 over x minus 3, does not exist. The two-sided limit does not exist. Over here, we have the limit as x approaches 4 of 2x over x minus 4 squared. So with the same idea, this top, or the numerator, having a degree of 1 and the denominator having a degree of 2, our denominator has a larger degree compared to the numerator. So we are again going to have a horizontal asymptote of y equals 0, and I want you to, I'm going to pause the video and just show you the answers, testing to the left of 4, just to the left of 4, and just to the right of 4, and see if you can't, pause the video and see if you can't come up with the infinite limit yourself as x approaches 4. Is it positive infinity, is it negative infinity, or does it not exist because the left and right limits are not equal? So I'm just going to step off and then slowly every couple of seconds or 5 seconds reveal the couple of parts of the solution. Okay, what we got? We tested the limit to the left of 4, and again, knowing that with the numerator and denominator just being simple polynomials, that we had that horizontal asymptote of y equals 0, the limit to the left, we plugged in just a little bit to the left, 3.9, got 780, so it seems like the function's increasing without bound. Not sure, just in case, check with your calculator, get a little bit closer, make sure that value is getting larger as you're getting closer to the value of 4 from the left, maybe 3.99, and we have the conclusion that our left limit is going to infinity. Same with our right limit. It also, as we approach from the right, I'm plugging on my test value of 4.1 in. I got 820, it seems to be, but I want to make sure, get a little bit closer, maybe 4.001, and show that that right limit is also going to infinity. So it seems like our function from the left and the right is going to infinity. Thus, we have a vertical asymptote at x equals 4. And the infinite limit, since the left and right hand limits are equal, the infinite limit is equal to infinity. And again, both these functions so far, or examples, have just had algebraic expressions. They're a little bit simpler than when trig functions start to get involved. Next example. Find any vertical asymptotes or removable discontinuities. Our rational function here has just simple polynomials in the numerator and denominator again, so this is kind of, again, falling back to our pre-calculus and Algebra 2 days of just finding or graphing rational functions. So our removable discontinuities are going to come from, in pure algebra, rational functions like this, it's a whole. So wholes come from factors, like factors that the numerator and denominator share, thus can be canceled out. So we're going to factor the quadratic on numerator and denominator. I'm going to do the first one and then sort of step out and reveal the factoring of the denominator to make sure that you remember how to do this on your own. When you have a quadratic with a leading coefficient other than 1, a very simple way of factoring it without having to do trial and error is to take your leading coefficient and your constant, multiply them together. I hope you already know this, but I like to do my videos quite thorough because it's not much of a two-way street here in questions. We're going to multiply the leading coefficient, the constant. We're going to get some product. This is just scratch work on the side. And we're looking for factors of this product that add to the middle term. And it could be negative 1 and 10. It could be 1 and negative 10. Or coincidentally on this one, we already have the factors that we need. Now what are we looking for actually? I didn't mention that. We are looking for factors of 10 that also add to that middle term. I think I said it but didn't quite clearly point what I was doing. I'm now going to take these factors and I'm going to use them to rewrite the middle term. So the numerator anyway is going to be 2x squared plus 2x minus 5x minus 5. And then I'm leaving the denominator blank for you to figure out. Now what we're going to do is we're going to start factoring by grouping. Factoring by grouping. Now what I mean is we're going to find a common factor out of the first two terms. Well, they're both divisible by 2 and they both have an x. So we're going to factor out a 2x. 2x squared divided by 2x is x, and 2x divided by x is 1. Now we're going to be looking for a common factor in the last two terms, and hopefully, if this is factorable, and it is factorable if we can find, again, leading coefficient, constant, get a product, if we can find factors of that product that add to the middle term, then it is factorable. So these two terms both have a common factor of negative 5. Now, my numerator has two terms in it, and both of those terms both have a common factor of x plus 1. So, if I again, kind of like I did in my two parts here where I factored out a common factor of the first two and last two terms, if I repeat that again, we get 2x divided by x plus 1, our common factor is going to be just 2x. And negative 5 times x plus 1 divided by x plus 1 is just going to leave us with negative 5. And these are all, of course, our f of x function that we're trying to, simplify. So you repeat the process of take the leading coefficient, the constant, multiply them together, find a pair of factors that add to the middle term and walk through this factoring, and I'll reveal it as well here in just a second. So we ended up with x plus 1 times 2x minus 5 over 3x plus 1 times 2x minus 5. In my work down here, what I wanted to make sure that you saw was my first two terms had a common factor of 3x. After I factored that out, I had in my parentheses, I had 2x minus 5. Well, my last two terms of the polynomial was a match of 2x plus, not plus 5, but minus 5. That means that when you factor by grouping, you have to show that you're factoring out a common factor of the first two and last two terms. Well, I don't want those to change because it was also already a match, so I factored out that positive 1 to show the factoring step and have the plus 1 show up with the 3x, but not change the 2x minus 5, so these two terms would have that common factor. Well, the 2x minus 5 canceled out, so it looks like this factor that's canceling out is going to give us a removable discontinuity at, let's see, well, the 2x minus 5, if that is equal to 0, and we solve it for x, we get 2x is equal to 5, we get x is equal to 5 over 2. So we have a removable discontinuity at 5 over 2. If you're interested, we can find the limit of the function at that value. The function is undefined at x is equal to 5 over 2, but we can find the limit of the function as it approaches 5 over 2 by using this function, which agrees with this function at all values except for c. So we can say that the limit as x approaches 5 over 2 of, and I'm going to use this function here, x plus 1 over 3x plus 1. Well, what is that going to be equal to? Well, this function is not undefined at 5 over 2. Again, like I said, this one is, so I can just plug it in. So we have, let's see here, 5 over 2 plus 1 over 3 times 5 over 2 plus 1. That is going to come out to be, we need common denominators, so this is going to become 2 over 2. And this is going to be 15 over 2, and we'll need a common denominator here, so we'll make 1 equal to 2 over 2. And we get 5 plus 2 is 7 over 2. We have 15 over 2. Plus 2 over 2. Well, 15 plus 2 is 17 over 2. And when we flip that denominator up to change the division into multiplication, we get 7 over 2 times 2 over 17, and that comes out to be 7 over 17. So, a removable discontinuity at x equals 5 halves, well, the limit of the function as x approaches 5 over 2 is equal to 7 over 17. Now, what do we have left? Well, we still have an algebraic function, a purely algebraic function. The numerator is a polynomial. The denominator is a polynomial. The numerator of the first, the numerator, let's try that again. The degree of the numerator is equal to 1. The degree of the denominator is equal to 1. And when graphing rational functions, if the numerator and denominator's degree are a match, then you have a horizontal asymptote that is equal to y equals, well, whatever your leading coefficients are. Well, that's 1 over 3. So now if you, because we still want to try and find vertical asymptotes, but this is just a simple, again, algebraic rational function. So using your information, your knowledge about graphing rational functions from Algebra 2 and pre-calculus, and knowing that we have a horizontal asymptote at y equals 1/3, we can find our y-intercept by letting x equal 0, and that's going to be 1. We can find our x-intercept by seeing where this function is equal to 0. Well, this function, we're going to set this equal to 0. How are we going to find the x-intercept? We're going to find out when this function equals to 0. The only way a rational function or a basic algebraic rational function can equal 0 is if the numerator is equal to 0. So we can set x plus 1 equal to 0, find that x-intercept, use a table of values to finish plotting the function. If you're in a class that doesn't allow you to use a calculator in your calculus class, if you are allowed to use a graphing calculator, well, you could just type that in and see what the function looks like. It will look like this. So with that table of values, we will see that the graph approaches negative infinity as you approach that value of, that x value of negative 1/3. I'm taking the denominator and setting it equal to 0 to find out what makes that denominator equal to 0, thus the function undefined. And the graph does approach negative infinity, again with a table of values or your calculator giving you a graph. Coming down on the other side as we approach, or approaching, this value of c of, or this value of x of negative 1/3, as we approach it from the right, the graph goes off to positive infinity, and thus we would say the infinite limit as x approaches negative 1/3 again does not exist, because the left limit is negative infinity, the right limit is positive infinity, and there is the whole, our removable discontinuity at the value of 5/2, 7/17. A graphing calculator will not show you that whole. You have to know how to find them yourself. You can use the table function of your calculator, but it's still only going to tell you where the whole is if it happens to actually include the x value where the whole is at. Next two examples will involve some trig functions and we'll be done with the video. Find the limit if it exists. We have the limit as x approaches pi/2 of x squared over the secant of x. Now, the secant of x, let's not forget on the unit circle, we plug in basically a rotation for trig functions. We plug in an angle measure rotation and we get out the sides of a right triangle. Well, secant is, gotta remember all those little x, y, r fractions. Secant is, well, reciprocal of cosine, right? Secant is r over x. So if you rotate pi/2 radians, or 90 degrees, your x value is 0. So the secant of pi/2 is 1 on the unit circle divided by 0, which is undefined. So this function is undefined at x equals pi/2. But does the limit exist? Like maybe it's a removable discontinuity, or does this limit just approach infinity, and thus we have a vertical asymptote at pi/2. Well, maybe I can manipulate this function to get another function which agrees with this function everywhere except at that value of c. And yes, secant is equal to 1/cosine. So the limit as x approaches pi/2 of x squared secant is 1/cosine. And then I can take that, you know, when you have basically a fraction, the x squared over 1, when you have something, a fraction over a fraction or a fraction in the denominator, let's not forget, again, this means division. So x squared divided by 1/cosine of x is the same as, or equivalent to, taking that denominator and flipping it up and changing the division to multiplication. So this just becomes the limit as x approaches pi/2 of x squared times the cosine of x. Now this function is not undefined at that particular value, so I can find the limit by just doing direct substitution. We got pi/2 squared, which is going to be pi squared over 4, times the cosine of pi/2. Well, I just said a second ago, and hopefully with my hand motion, showed you that the cosine of pi/2 is equal to 0. So, you know, then this is all just being multiplied together. So if one factor of a term is 0, then the entire thing is equal to 0, and that is the limit. The limit as x approaches pi/2 for x squared over secant of x is just 0. So this time with our denominator, and looking back at this again, our denominator is equaling 0, but yet we're not getting a vertical asymptote like we got with just the basic algebraic rational functions, where if the denominator was equal to 0 and the numerator was not, and it wasn't able to get factored away, we always got that vertical asymptote. Well, here, this 0 doesn't just sort of you know, factor away or cancel away with the numerator like it does look with algebra, but yet we, you know, and so we got this actual limit we could find of 0 instead of the normal. Hello, what am I trying to think of? Vertical asymptote. What am I teaching again? All right, over here we've got the limit as x approaches 1 of the cotangent of pi over x. Now there's not much we can do here, except maybe I could write this as cosine over sine, but probably the best way to try and find this limit as x approaches 1 is just simply to look at the graph. Well, remember, tangent and cotangent have a period of pi, not a standard period of 2 pi. So the period of cotangent is equal to pi divided by b, the coefficient of your independent variable. In that case, it's, again, pi, so the period is equal to 1. And if you want to graph a trig function and you don't remember exactly what it looks like, or this one's got a period change, then you can do a t-table starting with the phase shift and counting by 1/4 of the period. So we're going to say that x and y here. There is no parentheses with a plus or minus inside a parentheses, so there is no phase shift here. It's equal to 0. So I can start my t-table by doing 0. I want to count by 1/4 of the period, so I'm going to do 0, 1/4, 1/2, or 2/4, 3/4, and then finally 1, where we're trying to find the limit at. Well, the cotangent of 0, pi times 0 is 0. Now the cotangent is 0. Cotangent is x over y. So my x value is 1 and my y value is 0. So I'm dividing by 0. So cotangent of, again, plug in 0, multiply it by pi, that's 0. The cotangent is 0, it's undefined there. At pi over 4, the cotangent of pi over 4, that is, again, x over y, is going to be, looking on the unit circle, square root of 2 over 2 over square root of 2 over 2, which is equal to 1. So the cotangent of pi over 4 is equal to 1. The cotangent of 1/2 times pi, or pi over 2, the cotangent of pi over 2, the cotangent is x, which is 0, because I'm sort of, my shoulder's the origin, 0 over 1. So the cotangent of pi over 2 is equal to 0. The cotangent of 3 pi over 4 is -1, and the cotangent of 1 is, again, undefined. So it seems like we might have, and we are going to have actually, a vertical asymptote at the x value of 1. Graphically, it looks like this. We've got 0, we've got 1/2, we've got 1, we've got 1/2, 2/2, 3/2, and then finally we can go out to 2. At 0, we got a vertical asymptote. At pi over 4, we got a value of 1, so about right there we got a value of 1. At pi over, well, excuse me, I said pi over 4. At 1/4, we got a value of 1. At 1/2, we got a value of 0. At 3/4, we got a value of -1, so between 1/2 and 1, we got a value of -1. And then at the value on the x-axis of 1, we got an undefined value. And if we connect the dots and remember what our trig functions look like from pre-calculus or trigonometry, the limit of this function as you approach 1 from the left is -infinity. So just the fact that the trig function, the cotangent function, is approaching or decreasing without bound, is going down to -infinity as you approach 1 from the left, is showing that this is a vertical asymptote at x equals 1. But just to continue the pattern and understand the period, just to the right of the asymptote, we got a value of 1, so we're here. And another step forward of 1/4, we get a value of 0, and then again a value of 1. And then finally, again at the value of 2, we've gone a distance of 1, and the period of our cotangent function is 1. We get another vertical asymptote. So not only have we shown, with the function decreasing and increasing without bound as approaches 1, that we have a vertical asymptote, but we can also say that the limit as x approaches 1 of the cotangent of pi x does not exist, because we are approaching -infinity from the left and +infinity from the right. And now we've approached and found the end of this video. Thank you very much for watching. I'm Mr. True. Go do your homework.